Hey, and welcome to Algebra 2, Chapter 8. We're going to be starting on the unit circle for this chapter, and this is going to be section 8.1, which is going to be sine, cosine, and tangent. We're going to start here. It should be a little bit of a review from your geometry course, but we're going to cover some introductory topics just to make sure you're good. So let's take a look at what we're doing today. So with sine, cosine, and tangent, the first thing that you're going to be remembering is that anytime we're dealing with triangles, is that we have to deal with this special thing called the Pythagorean Theorem. The number one thing that most of you remember is that with a right triangle, let's zoom in a little bit. With a right triangle, if we have sides A, B, and C, we know that the Pythagorean Theorem, I'm going to do my best to spell this, states that a squared plus b squared equals c squared, meaning the sum of the square of the two legs of the triangle is equal to the square of the hypotenuse. So we have a squared equals b squared, or a squared plus b squared equals c squared. So let's try that out and let's do an example or two. So let's look at example 1. So our first example that we're going to be looking at is, let's take a look at the right triangle. And now this is not necessarily drawn to scale. So if I have a side length 3 and a side length 4, what is this side length? Let's zoom back in. So if I have side length 3 and a side length 4, what is the third side length? Well, according to the Pythagorean theorem, we know a squared plus b squared is c squared. Leg, hypotenuse. Well, I know that 3 is one of the legs because it's adjacent to my right angle, so I know it must be 3 squared, plus my other leg, which is the other side adjacent to my right angle, 4 squared, is equal to the hypotenuse, of which we don't know, so I'm just going to leave this as a c squared. And so let's see what c equals by finding the sum of these two. So 3 squared is 9, 4 squared is 16, 9 and 16 make 25. And the way to get rid of a square is by square rooting. So the square root of 25 is 5. And so my side length is 5. Works out nice and neat. So let's move over and let's take a second example, just to make sure that wasn't a fluke. So let's look at example number 2. Example number 2, again, now this is not necessarily drawn to scale. I can't draw these 100% accurately. So take my word that if I say that this is the square root of 3 and this is 1, that we're going to assume this is drawn accurately. So if I have side length 3 and side length 1 and I have my right angle right here, I know again, if I want to find out what this mystery side is up here, I'm going to have to use the Pythagorean theorem, which says a squared plus b squared is c squared, which means I'm going to take one leg length. I'm going to go with a is, again, this bottom one, square root of 3 squared. Now, could I have made a this top leg? Yeah, of course I could have, and it would have worked out the same because we're just adding them together. It doesn't matter if I have b first or a first, as long as I have the two of them. So I have the square root of 3 squared plus 1 squared equals this mystery hypotenuse, this mystery side. So let's see what we get. I know the square root and a square power cancel each other out, so I just have 3. 1 squared is 1, c squared. 3 and 1 make 4. And I know to get rid of a power, I use a root. So the square root of 4 is 2. 2 is equal to c. So having seen that, what we know is that the Pythagorean theorem works. It gives us the side of the third angle, or the third side. Now, I could use it for either one of these. I could have said I didn't know what a was, and I would have had a b squared and a c squared, but not an a squared, and solved for a instead. In this case, we solve for c on both of them, but let's move forward. So what we're going to be doing is, let's say instead of having just the sides of a triangle, let's say we're given something a little different. Let's say we don't have 2 of the sides, we only have 1. So now we're going to get into the actual signs cosines and tangents. We know that with a triangle, we need 2 bits of information, no matter what it is. So with a sine, the bit of information I need is I either need the angle. So I'm going to say sine of an angle. I'm going to rewrite this. Sine of an angle. I need the opposite side of that angle, and I need the hypotenuse. For cosine, the 2 things I need, so let's say the cos of an angle, I'm going to need the adjacent, and I'm going to need the hypotenuse. And for tangent, let's say I have the tan of some angle, I need the opposite, and I need the adjacent. So with these 3 things, this allows me to, in essence, miss one of them. So if I don't have the opposite and the hypotenuse, or if I don't have the adjacent and the hypotenuse, or I don't have the opposite and the adjacent, I'll need the angle. So I'm skipping out on one of the sides and I'm including an angle. So let's see what that looks like. Let's look at our first example. Now our first example is, let's take a look at a triangle. And this triangle right here, again, it's a right triangle, so we know we can use these theorems. And I only have a side of 14. And I can't figure out what these other sides are, because if I wanted to figure out what this side was, I'd need these 2. If I wanted to figure out what this leg was, I would need these 2. So I don't have enough information. The only way I can solve this is if I either have another side length or if I have an angle. Doesn't matter which angle, as long as I have one of them. In this case, I'm going to give you this angle. So let's say I know it's 67 degrees. Now I have enough information to solve this. So let's take a look. If I have 67 degrees and I want to find out what this length is, I know this is a leg, and so these are going to be my A's and B's. Let's assume this is A, so I'm going to say this is B, which means my hypotenuse must be C. So if I want to find what B and C are, I'm going to need to use a couple of these formulas up here. At 67 degrees, I have the leg that is adjacent. So I know I have my adjacent. So I have one of 2 things. I either have cosine or I have tangent. So then I got to look, if I have cosine, I must have the hypotenuse. And if I have tangent, I'm looking for the opposite. So let's see what I'm looking for first. If I have the adjacent and I'm looking across, I'm looking opposite. So what deals with opposite and adjacent? Tangent does. So I'm going to fill this out and say, hey, the tangent of 67 degrees is equal to the opposite, B, over the adjacent, 14. And that's enough information to solve this. So I'm going to solve for B by saying I'm going to multiply times 14 on both sides. They cancel out. So I have 14 times the tangent of 67 is equal to B. I plug this into the calculator, and what I get is I get approximately 32.98 is approximately what my B value is equal to. So I know what B is. Now let's go for C. So if I want to find C using my 67 degree angle, I have the adjacent side, meaning the leg that is connected to it, and I'm looking for the hypotenuse. So which one deals with adjacent and hypotenuse? No. Cosine. So let's write that one out. So the cosine of my angle is equal to my adjacent, which is 14, over my hypotenuse, which is C. And now, unlike this one, which was easy, where I just multiplied by the bottom, we notice my 14 in this case is on top. So I'm going to have to do a little maneuvering. Now I can cancel out this fraction by multiplying both sides by c, which gets rid of the fraction. So I have c times the cosine of 67 is equal to 14. But I didn't actually solve for c there. I just moved it. So now what I've got to do is I've got to move this over there. How do I get rid of multiplication? I divide it. So if I divide both sides by the cosine of 67, those cancel out. That means my c is equal to 14 divided by the cosine of 67 degrees, which means my c is roughly equal to 35.83. And remember, when I draw the squiggly equals, that means that I've rounded here. This is actually 35.83, and then there's several decimals following it, but we're not going to put those. So I found that b equals 32.98 and c equals 35.83. Does it work? Do using these relationships make those side lengths true? Well, there's a way to check it, and we're going to check it using the Pythagorean theorem. So let's try this out. Let's check our work. Now, I know checking our work is going to be a squared plus b squared equals c squared. So what we're going to do is we're going to say, hey, I'm going to have a 14 squared plus my b squared, which is 32.98 squared, equals my c, which was 35.83. And let's check this out. So now my 14 squared is going to be 196. 32.98 squared, if I plug that into the calculator, I get 1,087.68. And again, if I plug this into the calculator, now realize I'm rounding a little bit here. So is my answer going to be 100% exact? No, unless I plugged in 14 tan 67 squared. So realize I'm going to get an answer that's going to be almost the same, the way that I'm doing this right here. So let's take a look. If I have 35.83, if I square that, I'm going to get 1,283.79. If I add these two up, I get 1,283.68 is 1,283.79. Are those almost exactly the same thing? Yes, I'm a few decimals off, but again, I'm assuming the fact that because I rounded these, my answer is not going to be 100% exact. In fact, if I rounded these, I'm getting the same thing. So know that yes, this checks out. This works. So now my answers are in fact correct. And so this is where we want to focus. So let's do another example. Let's do a second example. So for my second example, let's not give you the adjacent side. Let's give you something else. So let's give a triangle that looks a little something like this. I have my right angle, and I have, in this case, the hypotenuse. I have the thing that is opposite my right angle, which means I'm trying to find my A and my B. Fortunately, I don't have enough information at this point, but what I can do is I can plug in an angle measure. And if I have an angle measure of, let's say, 14 degrees, now I have enough information to solve this. And let's see what we can do. So I know because these are my legs, these are going to be A and B. My legs are on each side of the right angle. The hypotenuse is always opposite the right angle. So let's see what we have. If I have 14 and I want to solve for A, is that the adjacent side or is that the opposite side? It's the adjacent. So 14, what we're looking at, what deals with adjacent and hypotenuse? Well, sine deals with opposite and hypotenuse. Cosine deals with adjacent and hypotenuse. And tangent deals with opposite and adjacent. Which one deals with adjacent and hypotenuse? Cosine. So I know the cosine of 14 degrees is equal to A, which is adjacent, over the hypotenuse, 40. Oh, this one's going to be pretty easy. You just multiply both sides by 40. They go away. So 40 times the cosine of 14 is equal to A. And again, I'm going to round this because when I plug it into the calculator, I get 9 point, whoop, did that backwards. I was looking at the wrong answer. 38.81 is roughly equal to A. And we're going to check this out later on. But the next thing we're going to solve for is I want to solve for B. And I know B isn't adjacent. It's not the leg touching my 14. It isn't touching 14 at all. So it must be opposite. So I'm either dealing with sine or I'm dealing with tangent. So if I have the opposite and the hypotenuse, opposite, opposite. This one deals with opposite and adjacent. This one deals with opposite and hypotenuse. So I must be dealing with sine. So sine of 14 degrees is equal to, we said that was opposite over hypotenuse. So B over 40. Hey, both of these are solved pretty easy. I can just multiply by 40, multiply by 40. So 40 times the sine of 14 is equal to B. Now if I plug that into the calculator, 40 times the sine of 14 is going to be 9.68. And again, this is roughly equal to, I've rounded, it's actually a really big decimal, but we're going to use these two. So that means that when we check our work, when I plug in my A and my B and see if it equals 40, I'm going to get something that's really close to 40, but because I've rounded, it's not going to be 100% exact. So let's try this. Let's check our work. If I know A squared, 38.81, plus my B squared, which is 9.68, it should equal my C squared, which is 40. If I multiply 38.81 squared, I get 1506.22. If I square 9.68, I'm going to get 93.7. And if I square 40, I get 1600. And so let's see what happens with that. If I add these two up, I get 1599.92. Now again, like I said, we rounded up here. So am I going to get exactly 1600? No, but is that really close? Yes, this checks out. Our answers are in fact good. Now if I got something like 1200, would 1200 be really close to 1600? No. So if you get something like 1200 is equal to 1600, we know, no, we did something wrong. And so we'd have to go back and we'd have to check and see, did I screw up on A or did I screw up on B? But because these are almost exactly the same, I know the fact that my rounding errors means that these are going to be exactly the same if I used all the decimal places. Cool. Okay. Now let's do one last example, one where it doesn't have a rounding error, because a lot of you are like, well, if it doesn't equal, when does it not equal? So let's look at one that works out nicely. So my third example is going to be something that looks like, let's see, if I've given you adjacent and I've given you hypotenuse, how about I just give you the opposite this time? Let's make it something interesting. The square root of 3. And I'm going to give you 60 degrees right here. Probably should have drawn that a little bit bigger, but oh well. So if I have a triangle with 60 degrees and the square root of 3 is the opposite, I want to find my adjacent side and I want to find my hypotenuse. So 60 degrees, if I have the opposite and I want to find the adjacent, which one would that be? Sine deals with opposite and hypotenuse. Cosine deals with adjacent and hypotenuse. And tangent deals with opposite and adjacent. So if I'm dealing with opposite and adjacent, that means that I must be dealing with tangent. So if I have the tangent of 60 degrees is equal to the opposite over the adjacent, opposite over the adjacent, square root of 3 over A. Okay. Now this is one of the fun ones where it's 2 steps instead of 1. I have to get rid of the fraction by multiplying times A, and it cancels out over here. But did I solve for A? No. Because what a lot of you want to do when you see this is you'll multiply by the square root of 3, and you'll try and cancel those out. But square root of 3 times square root of 3, does that disappear? No. It doesn't cancel out the a, doesn't cancel out the square root of 3. It just makes that 3 over a, which is still a fraction. You have to multiply by the bottom to get rid of it, which means my bottom is now up top over here. So if I have a times the tangent of 60, what I'm going to have to look at doing is I'm going to say, okay, a times the tangent of 60, I get rid of that by dividing by the tangent of 60. That cancels out over here. Now my a is isolated. So I have the square root of 3 divided by the tangent of 60. And so my a, in this case, is equal to 1. No rounding, no decimals, just 1. Okay. Now let's look at finding c. Now if I need to find c, I'm dealing with, I have the opposite and I have the hypotenuse. Which one deals with opposite and hypotenuse? Sine. So I'm dealing with the sine of 60 degrees. And sine of 60 degrees is the opposite, square root of 3, over the hypotenuse, which is this unknown value of c. Now again, this is just like what we did over here. I can't multiply by a square root of 3 to get rid of it, but I can multiply by c. Gets rid of that. So c times the sine of 60 is equal to the square root of 3. Over here I divide by the sine of 60. Gets rid of those. And so c is equal to the square root of 3 divided by the sine of 60 degrees. There we go. And if I plug that into the calculator, my c, in this case, is equal to 2. So if I have a 1 and a 2 and a square root of 3, I wonder how that would look if I checked it out. So let's check it out. So if I know a squared is 1 squared, b squared, which is my square root of 3, is going to be equal to my c squared, which is 2. Let's see what we get right here. I know 1 times 1 is 1. I know a root and a power are going to cancel each other out. So I'm left with just 3. And 2 squared is 4. Does 4 equal 4? Yes, it checks out. So in this case, because I didn't need to round on either one of these, I see the fact that I'm getting exact answers. Unlike before where I had to round on my a and my b, which gave me this is almost equal to, but I knew that it's going to end up being roughly the same. Here I didn't need to. This checks out equally. I have a 1, 2, square root of 3 triangle. We're going to be seeing more of that guy later on. But in that case, that is 8.1. That is an introduction to the unit circle, sines, cosines, and tangents. I'll see you next time.